In this video, we will look at an optimization example where we minimize the cost. So this is a problem from worksheet 9. It's question number 11. So just for reference, so here is worksheet 9 on sections 5.1 and 5.2. So there are a bunch of optimization practice problems here. And we're going to be looking at question number 11. Question number 11 from this worksheet. Okay, so that worksheet is posted on Camino. Alright, so here is the example. It says that a cylindrical can is made out of two types of metal. The top and bottom cost $5 per square inch, and the lateral surface costs, this should say costs, $2 per square inch. If the volume of the can must be 12 inches cubed, find the dimensions of the can, so radius and height, that minimize its cost. So a couple of things that are going to be useful for us to recall are the formula for the volume of a can, of a cylinder, and the lateral surface area. All right, so we want to begin any optimization question by first identifying what is the thing that we want to minimize or maximize. And this question says we want to minimize the cost. So we are trying to minimize the cost. Okay, so if I were to draw a picture of this scenario, so we have this cylindrical can, so okay, we have this circular top, and then going down, and then we have the bottom, the base. Okay, I'll draw a dash line for the back of that I can't really see. Okay, and then let's draw in a radius. So I'm labeling the variables that I'm going to need in this problem. Okay, so one is the radius. The other variable is I'm going to call the height h. So the height, I'll call it h. And ultimately, it's my goal to figure out what r and h are that minimize the cost. Okay, so I've identified what my objective is going to be, cost. I need to minimize the cost. I've drawn a picture. We are ready to write down the objective equation now. All right, so our objective equation, so we need to write down an equation for the cost. So I'll call it C for cost. So the top and the bottom surfaces have a different price per square inch than the lateral surface on the side does. So it's $5 per square inch for the top and for the bottom. So this is going to multiply the area of the top and the bottom, so I'll say plus the bottom. And the area, we're measuring that in inches squared. And I'm writing the units here just so I can better see how they will cancel. So the inches squared on the denominator in this first parentheses are going to cancel the inches squared in this next parentheses. Okay, so this is going to be my cost for the top and for the bottom. Okay, and then I add to that how much the lateral surface is going to cost. So it's $2 per square inch, and that's going to multiply the area of the lateral surface, the area of the lateral surface again in inches squared. So again, the inches squared are going to cancel here. So let's plug in for these areas. So we get the cost equals, so we are going to get 5. At this point, I'm going to stop writing the units. I'm just going to focus on the numbers that I have. Okay, so I have 5, and then the area of the top is pi r squared. That's the area of that circle. The area of the bottom is also pi r squared, because it's a circle as well with the same radius. Okay, and then we have plus 2 times the lateral surface area. But the lateral surface area is 2 pi r h. And simplifying this, we get C equals 10 pi r squared plus 4 pi r h. And that's our objective equation. All right. So what we were hoping is we want this in terms of just one variable. So right now we have the cost in terms of R and in terms of H. We want just one variable on the right-hand side. Okay, and then the way we get it in terms of one variable is we use the constraint. So we need to use the constraint next. Okay, so at this point, pause the video for about 4 minutes to see if you can continue the problem from here. So we've looked at a few optimization examples in the last lecture video. So this is something that we've seen before, these optimization questions, and we've gotten started together. I want you to pause the video for about 4 minutes to see if you can continue it. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 4 minutes. Alright, so hopefully you've done that. Hopefully you've paused the video for 4 minutes to try this. Let's talk about it together. Okay, so I've got my objective equation written here. And so now let's write down the constraint. So the constraint. So the other piece of information that the problem tells me is it tells me the volume. The volume is 12. And that's going to be my constraint. So the formula for the volume of a cylinder is pi r squared times h. So we have pi r squared times h equals 12. So now I need to solve for one of these variables, either h or r, in this constraint equation, and then plug that into the objective. So we have choices. So I want to briefly talk through which one's better, because it turns out one of them is a little bit better to solve. And I want to talk briefly through how do we know which one's better. Okay, so I'm going to talk about it if we do it both ways so we can figure out which one's going to be better. Okay, so first let's solve for h, and then we'll solve for r. So if we solve for h, if we get it by itself, we'll get h equals 12 over pi r squared. And now we would substitute this into the objective. So doing that, we would get that c equals 10 pi r squared plus 4 pi r, and now I plug in for h. So if I do that, I will get 12 over pi r squared here. Okay, so not too bad. We were able to solve for h without much trouble and then plug that in for the one occurrence of h in my cost equation, in this objective equation. All right, so what about if I solve for r instead? Well, if I isolate r squared, I get r squared equals 12 over pi h. And then I could square root this. If I square root both sides, I get r equals the square root of 12 over pi h. And you might be wondering, wait, did I forget my plus or minus? It turns out here I don't need a plus or minus, since r is my radius, and my radius can't be negative. R can't be negative. It wouldn't make sense for my radius here to be a negative number. Okay, so I actually don't need to worry about the plus or minus. When I square root this, I can just write the positive root. All right, and now I got r isolated. Let's substitute this into the objective now. So let's sub into the objective equation. All right, so if we do that, we will get c equals 10 pi, and I'm going to have to square r. So I plug in r, which is square root of 12 over pi h. So that's not too bad, because when I square this square root term, the square root will cancel. Okay, and then we have plus 4 pi r, so plug in, so square root of 12 over pi h, and then times h. So we have this. So the first term within this isn't too bad because the square root will cancel. But in the second term, the square root won't cancel. So overall, I would say doing it this second way looks This looks more tedious. This looks more tedious. I'll put a sad face. Whereas this first way, where we solve for h and then plug that in, this looks easier. This looks easier. So there are a couple ways that I could have recognized this without having to do each one first and then figure out which one looks better to me. So one is, if we go and look back at our constraint equation, we could hopefully see in our head that when we solve for h, we won't get a square root. But when we solve for r, because of the squared, to get rid of the squared, I'm going to end up with a square root. So that's one thing to look for in a problem. When I solve for one of my variables, will I end up with something more complicated, like a square root? And that happened when we solve for r. The other thing that I can look for is, in my objective equation, r occurs twice in the r squared and in the 4 pi rh, but h only occurs once. So because h only occurs once, it's going to be a little bit easier to just plug in for the h, because I only have to plug in something once there. So I would say those are the two tip-offs on how I could have recognized it was going to be better to solve for h without having to do both of these steps. Okay, so I'm going to continue down the easier route. So we get the cost equals 10 pi r squared plus, and with the next term, we'll get a little bit of cancellation. 4 times 12 is 48. The pi's will cancel, and one of the r's will cancel. So this r will cancel away, and on the bottom, I'll be left with an r. So we get 48 over r. All right, so that's my cost function. And we got it in terms of one variable. So once we have that, now we are ready to find our critical numbers. Find our critical numbers. So we are going to need to take the derivative of this. So to take the derivative of 48 over r, to avoid quotient rule, I can rewrite this as 48r to the negative 1. And now I just have to use power rule there. No quotient rule needed. Okay, so let's take that derivative. So we'll get the derivative of cost. For the first term, I will end up with 20 pi r. And then the derivative of the next term will give me negative 48 r to the negative 2. All right, so let's simplify this derivative a little bit. Okay, so this equals 20 pi r. And let's rewrite this negative exponent by bringing it to the denominator. So I'll get minus 48 over r squared. And now to combine these, I can get a common denominator. So to get a common denominator, I would multiply this first fraction by r squared over r squared. So I would multiply it by that. So that'll end up giving me 20 pi r cubed minus 48 over r squared. I'll write that a little better. So this is r cubed. Okay, so we got our derivative. I've simplified it a little bit. Now we want to find where the derivative equals 0 or the derivative is undefined. I need to find all places where the derivative is 0 and all places where the derivative is undefined. Okay, so let's talk about undefined first. Usually that's quicker to identify. So this is going to happen when the denominator is 0 of my derivative. So that occurs when r equals 0. But one thing that I have to be mindful of is if I go and look at my looking at that original function for c, I'm not able to plug in 0 for r because it makes this fraction 48 over r undefined because the bottom would be 0. So r equals 0, what I want to note about this is not in the domain of the original function. C equals 10 pi r squared plus 48 over r. So r equals 0 is not going to be a critical number. Even though it makes my derivative undefined, it's not in the domain of the original function, so it can't be a critical number. All right, so now let's find when the derivative is equal to 0. All right, so we will set 20 pi r cubed minus 48 over r squared equal to 0. And then I want to solve this. So I can multiply both sides by the denominator, r squared, to get rid of the fraction. So if I multiply both sides by r squared, we end up getting 20 pi r cubed minus 48. So r cubed minus 48 equals 0. And now if I move stuff around, I can isolate for r cubed. We'll get r cubed is equal to, let's move the 48 to the right, and then I'll divide by 20 pi. So divide by 20 pi. And I could simplify this fraction a little bit. I could divide the top and the bottom by 4 and get 12 over 5 pi. So we have r cubed equals 12 over 5 pi. And now cube rooting both sides, we get r equals the cube root of 12 over 5 pi. So we ended up with one critical number here. It's just r equals the cube root of 12 over 5 pi. So next, what I'm going to do is think about the interval for my variable. So the interval for r, so r is my radius here. And with my radius, I might think, wait, if r equals 0, I would get sort of a degenerate cylinder. It would be a cylinder that has no radius. And we've seen that we can get degenerate things before. But in this problem, it turns out that r being 0 is not allowed, and I'll talk about why. So I'll put a parenthesis at 0. And then r could be as big as I want. It'll go onwards towards infinity. R can't be negative. It doesn't make sense for my radius to be negative. So why is r not allowed to be equal to 0? So r is not allowed to be equal to 0 since if r does equal 0, then we have an issue with the volume. Then the volume would be equal to 0, but we're given the volume. We are given that volume equals 12. So that's why r is not allowed to be equal to 0 in this problem. Even though that would give us a degenerate cylinder, which sometimes is okay. In this problem, it's not okay because the volume was given to be 12. All right. So we have this open interval, which means we have to do this using our number line method. Okay, so now we have to test our critical numbers. So we're going to use our number line method to test these critical numbers. Okay, so I'll draw a number line, and I'll put a critical number on there, which is cube root of 12 over 5 pi. There's also sort of like a natural boundary for the smallest r can be. The smallest it can be is 0, and it's not allowed to be equal to 0, so I'll put a little parentheses where 0 is. I don't want to plug in any negative numbers for my test points, because r is not allowed to be a negative number here. All right, so I want to keep track of my derivative and my original function. All right, so I'm just going to scooch that up a little bit, and I'm going to make my table. So I'll draw some lines, I'll make my table. So let's remind ourselves that the derivative of c prime, was equal to 20 pi r cubed minus 48 over r squared. So that was our derivative after we had simplified it. So now I need to pick some test points. I need to pick a test point that's smaller than this cube root, and that's larger than this cube root. So one more time, I'm going to ask you to pause the video, this time for just 1 minute, to see, can you identify a couple of test points, something smaller than this cube root, something larger than this cube root, without a calculator. It is definitely doable without a calculator. So I want you to pause the video and think about that for a minute. 4, 3, 2, 1, pause the video. Pause the video for 1 minute and see if you can determine a couple of test points without a calculator. All right, so hopefully you've paused it and tried that for a minute. So if I want a test point, a value for r that's smaller than this cube root, what I can do is I could change the numerator, the 12, and just make it smaller. So I could do the cube root of, say, 1 over 5 pi. And that's definitely going to be smaller than the cube root of 12 over 5 pi, because I've made the numerator smaller while keeping the denominator the same. So I'm going to use that same idea on this side. If I want something larger than it, I'll make the numerator larger. So maybe instead of 12, I'll pick something sort of nice and round, like 20. So I'll do cube root of 20 over 5 pi. And that's how I could get around without having to use a calculator for my test points. So now let's plug in these test points into the derivative. So let's first plug in cube root of 1 over 5 pi. So if we plug that into the derivative, we'll get 20 pi. And then I take my cube root of 1 over 5 pi and cube that, minus 48. And then over r squared. So r, the key thing that I care about for the denominator is this test point is positive. So I'll have a positive number squared. That's what I care about the most on the denominator. Okay, so on the numerator, the cube root and the cube are going to cancel. So the cube root and the cube are going to cancel. And then 20 pi gets multiplied by 1 over 5 pi, which gives us 4. We have 4 minus 48 over a positive number. So the numerator is negative, the denominator is positive. Overall, that's negative. All right, so my derivative is negative on this side, which means the original function would be decreasing. So it's going down like this. All right, now let's plug in our other test point. So c prime of the cube root of 20 over 5 pi. So 20 over 5 pi. So plugging this in, we'll get 20 pi times the cube root of 20 over 5 pi cubed minus 48. And on the denominator, I'll have the same r value, but I am going to square it. And this r value is a positive number, and I'm going to square it. Okay, so just as before, the cube is going to cancel this cube root. All right, so I know that when I take 20 pi and I divide it by 5 pi, I'm going to get 4. And 4 times this 20 on the numerator is going to be 80. So I'll get 80 minus 48 on the numerator and a positive number on the bottom. So the numerator is positive, denominator is positive, so that makes this whole fraction positive. All right, so my derivative is positive on this side, which means c is increasing. C is increasing, it is rising like this. So when my function changes from decreasing to increasing at a critical number, and I know this is a critical number, I know it's a critical number because it made my derivative equal 0, and this r value is in the domain of the original function. This r value, this cube root, doesn't make this denominator of c equal 0 like r equals 0 did. That's why r equals 0 was not a critical number. All right. So now we are ready to justify why this critical number isn't just a local max, because usually the number line tests for local mins and local maxes, why it's an absolute max. All right, so we would say that C has an absolute min, and whoops, I think I was saying local max when I had meant to say local min, and I was saying absolute max when I had meant to say absolute min. Because based off of my picture, when my function changes from decreasing to increasing, that corresponds to a local min, not a local max. All right, so I just wanted to clarify that. Okay, so this local min happens to be an absolute min. There's an absolute min at r equals cube root of 12 over 5 pi, since c is decreasing for all r less than this number, less than the cube root of 12 over 5 pi, and it's increasing for all values of r that are greater than the cube root of 12 over 5 pi. All right, so that's justifying why it's not just a local min, because that's what the number line usually does. It just tells us what the local mins and the local maxes are. But in an optimization question, we always want absolute mins and absolute maxes. So this justification is necessary whenever I do an optimization question using the number line to justify why it's a min or max. Okay, so the final part is to make sure I answer what the question wanted. So if I go back and look at the question ultimately said, find the dimensions of the can, find the radius and the height. So I need to make sure I find the radius and the height. Okay, so the question wanted the dimensions. Okay, and I got one of the dimensions. I got r. R is the cube root of 12 over 5 pi. And they're units. I should include those now. This is inches. So to get the height, we can use our constraint. So remember, our constraint was that the volume, pi r squared h, equals 12. 12 inches cubed. So if I solve for h here, h is going to be equal to 12 inches cubed over pi r squared. And now I can plug in the radius here. So I get 12 inches cubed over pi times the radius, which is cube root of 12 over 5 pi inches. And I got to square that. All right, so we have h equals, we'll have the 12 on top. And on the bottom, we'll have pi. And then if I rewrite this cube root being squared as just a fractional power, this is 12 over 5 pi to the 2/3 power. A 2/3 power means I'm going to square this thing, but also cube root it. And that's what I have here. So finally, there we had inches cubed on top, inches squared on the bottom. So those will cancel and just give me an inch. So those are the units of height. They're inches. So we have the radius of this optimal cost can, and we have the height of this optimal cost can. So that is my answer. So in the next video, we will look at another optimization example, but where we maximize profit.